Hi, Chesney Culver here. My group members and I are going to be discussing Hooke's Law. We're all enrolled in Physics 1305, Section 2E1, and this is the fall semester of 2025. So just getting started here, I'll go ahead and move into our introduction about Hooke's Law. Perhaps if my slides want to move. Okay, so my portion of the introduction, we're just going to talk about Hooke's Law, a little bit of background, couple definitions, things like that. So basically, Hooke's law, it's also known as the law of elasticity, is super important in physics. Hooke's law is a directly proportional relationship talking about force, which we're going to call variable F, on a material and the deformation, aka delta L, that it's going to cause. Hooke's law can be written as an equation, that equation being F equals K times delta L. So let's break down that equation just a little bit. So like I said earlier, force is going to be F represented by the variable F. Okay, then we said deformation delta L. So when we're talking about deformation, we've defined it earlier in the course, but just as a reminder, deformation is talking about the change in something. So if we look over here at this specific example, we have a spring. So the spring starts out here. It has no force being applied to it. And then we can look at the next spring over here. Now the spring has a force of 1 unit. We're just going to call that ball a unit. We have 1 unit of force being applied. We have that weight or that mass there being affected by gravity and pulling that spring down. So now you notice the spring is stretched because we have this weight pulling on it. Now here, off to the side, we see that distance is marked as x. Depending on which text you're using, where you're researching, different places call deformation different variables. Later on in this slide, I'll use y. Some places use x. Some places use delta L, meaning the change in the length, because all delta is change in something. So just depending where you're looking at, you're going to see different things. But pretty much all it is for Hooke's law is force is going to equal some k times some change. So over here, they use it, the spring of the force equals negative kx. We'll talk about why it's negative here in a second. But pretty much when we're talking about delta L, we're just saying how much did it change, okay? So then over here, we applied 2 units of force. They call it F2 or 2F. And we see that that string is now stretched twice as far. The deformation is twice as long. Um, so that's just a couple of things there. This law is super helpful because it actually helps us calculate the amount of force needed to compress or stretch a spring. It also tells us a lot about movements, certain types of movements, which I'll get into more a little bit later on. But anyway, a couple definitions that will be helpful further along in our presentation is one, elasticity. So when we talk about elasticity, that is just the material, a property a certain material object has that basically says how it's allowed to return to its original shape and size once it's been deformed by an external force. So looking back at this spring example, once we added those units of weight, the elasticity that spring has is its ability to return back to its original form, which is this spring here on the left. Definition 2 talks about an external force being defined as any force that acts on an object outside of an system. Um, or outside of its boundaries. So again, going back to the example we had here on the screen, talking about those red balls that I called units because we don't really know how much they weigh, those would be an example of an external force because it's deforming our spring. One other thing I wanted to mention while we're still on this slide is I kind of breezed over K with the variable K when we were talking about Hooke's law. That is just constant. I think we said before in the class that it comes from maybe a Greek word or Latin word, or it might have been German now that I think about it. But regardless, K just represents a constant. Typically, it's given to us in our textbook. We talked about a bunch of different spring constants. Those are just what's going on there. K is a constant number typically given by the problem or by the textbook. In some places, you might notice, like on my slide here, it's a positive K. In other places, like on my image over here, it's a negative K. remember when we're talking about mathematics, guys, a positive and a negative is just telling you kind of a directional term. So if you're thinking about a number line, positive is going to be on the right-hand side of the number line, which I believe the right's going to be this side for y'all. And then when we're talking about a negative, it's going to be the opposite direction. So if you see a negative K some places in the slides and you see a positive K in other places, just know that's kind of where that is coming in. It's just a directional term. It kind of tells us if we're talking about compression of a spring or expansion of a spring or stretch of a spring. Okay. So, my introduction slide continued, just some basic facts about Hooke's law. One thing that I found was really interesting was Robert Hooke, who's a scientist who is credited with finding Hooke's law, originally published it under an anagram. This guy right here, the CEIII da 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 da. 2 years later, after its publication, he revealed the meaning, which I'm not fluent in Latin, so I'm sorry if I butcher this, to tenso sic vis, which is Latin for the extension and so the force. So if we go back to the last slide, we talked about force being proportional, which kind of makes sense why he named it this. As the extension, so is the force. So if we talk about a proportional relationship, all that's really saying, guys, is if you do something to this one, you should expect that the other will be affected by the same amount, right? So if we're talking about multiplication, if I multiply this side by 2, then the other side will also be multiplied by 2. It's a proportional relationship. They affect each other at the same rate. Um, so really cool how he named it that. And if you notice that this anagram is just these letters here alphabetized. So the reason he did that was because back in the 1600s, when Robert Hooke made this discovery and was researching these things, it was a very competitive field. It still is. And he wanted to claim responsibility for Hooke's law and be known as the one who discovered these things, but he wasn't quite ready to make those discoveries known. So one of the ways he was able to do that was publishing it under this anagram, and there was a record of it. And then he was able to later go back on, continue his research, finalize things, get them how he wanted to present them, and then was able to publish it under the original title, as for the extensions of the force. So really, really cool stuff. And later on, I'll even talk about how a different scientist was credited, almost credited with some of the very similar things. So, interesting fact was Hooke's law is the first classical example of an explanation of elasticity, which is pretty cool to think about. So, anyway, that is my introduction. All right, Chesney Culver again, just here to talk about my related field. Again, we're talking about Hooke's law. So the field I chose that's related to Hooke's law is something called differential equations. So, different or Hooke's law is actually used in a lot of fields of mathematics. It's seen a lot in calculus. It's seen a lot in a specific type called differential equation. So, differential equations is basically just the mathematical study of equations and that relate to functions and their derivatives. So, derivatives might be a little bit outside the scope of this course. It's more of kind of a calculus concept. But basically, what a derivative is it's just measuring a function at an instantaneous rate of change or at a specific point. So if you've taken math classes before, maybe you know that when we talk about rate of change, that's just another way of saying the slope, right? That's the steepness of a line, if you remember that maybe from a math class. So when we're talking about measuring that function at an instantaneous rate of change, that's actually talking about a special type of line known as a tangent line. So we're looking at the slope of a tangent line. Again, a little bit outside of the scope of this class, but for the purposes of what we have to talk about here for Hooke's law and how it relates to physics, I just want to make the point that when we talk about a derivative, again, talking about the rate of change at a specific point, aka the slope, we're going to talk about something called a first derivative. This is when you take the first time you take a derivative, and again, more of a calculus concept. You can have a first derivative, second derivative, third derivative, and so on and so forth. But what's really cool about the first derivative is it's actually just talking about velocity, which is how it's important to us, Hooke's law in physics. Um, Because all a derivative is talking about the rate of change of a position of an object. So when we're talking about rate of change of a position, again, that's just how we define velocity. So once we take that first derivative and we find the velocity, we can take the second derivative. And when we talk about taking the rate of change of a velocity of an object, we're actually talking about acceleration. I'm just going to do some hand waving and go from there. But anyway, first derivative, second derivative related to velocity and acceleration. So the reason it's important to differential equations is what we're going to do is we're going to take Hooke's law, which we talked about on the introduction slide. F equals k of x. Sometimes it's negative, sometimes it's positive. Again, just talking about directional terms there. And instead of using delta L like we did on that first slide, I'm going to call it X, just like we did on that first slide, how I talked about it, just to make things a little bit easier and we're not throwing around Greek letters and a bunch of variables. So let's just say F equals negative K times X. And then we're going to take something else we talk about in this course, and that's Newton's second law of motion. And that law basically says force is equal to mass times acceleration, F equals ma. So once we use some algebra, we can and take some derivatives, we can find that since the force here, right, F equals k of k, negative k times x, and force here equals ma, those two things are equal. If force equals this and force equals that, force is just force. So those two things that we're saying are equal to force are going to be equal to one another. And that's what we're doing here. Now notice the second derivative thing popped up here. That's some calculus-y stuff coming in there, but I'll wave my hands and hope that everybody can trust me when I say that F equals mass times the second derivative of our, the word is slipping from me, deformation, sorry y'all. So we have force equals our mass times our change in our length, our deformation, equals our negative constant times our original deformation. So again, here we're talking about how x is the second derivative, aka acceleration. And the reason we care about this formula, guys, is because using Newton's law and Hooke's law, I'm sorry, Newton's second law, I should say, and Hooke's law, we can combine those things to actually help us predict certain types of motion. And these motions are what we call simple harmonic motions. And basically, a simple harmonic motion is going to be anything that vibrates or swings or wiggles or moves in some kind of wavy pattern. And what's really cool about this is there's lots of motions out there in physics, in real life, that we're able to estimate their behaviors using Newton's second law and Hooke's law because of these calculations, right? So again, a little bit outside of the scope of the course with the derivatives and things of that. But it's really, really interesting and really, really cool because differential equations and using those second derivatives really helps us understand the world around us. And just like I said, we're able to predict those behaviors. We're able to predict behaviors of simple harmonic motion and elasticity, which is that stretching motion yet again. So I have this image over here that's basically kind of talking about that. Hooke's law is just a second order differential equation. Okay, they sometimes call them DE. Um, this model is showing simple harmonic motion. So basically anything that has a spring, a tire on a swing, a clock. We'll talk about that in a little bit here in a second. We'll talk about the simple harmonic motion there. But what Hooke's law is basically says, it can tell us the force needed to stretch that spring and predict those behaviors. So it's pretty much that it's proportional to the distance of y. Again, we talked about the proportionality aspect of Hooke's law in that introductory slide. If you notice here, this looks a little bit different. In math, there's a couple different ways we can denote a derivative. This d squared and dt squared, that's just the derivative right here. We also can use what's called a prime, that little tick mark there. So this is x prime prime. All that means is derivative, guys. So if you see m times x tick tick, second derivative, or if you see this symbol right here, d squared y over dt squared, again, just a second derivative with respect to y. And again, k is just our constant. So hopefully that wasn't too much. We're too much there, but just super interesting stuff. It, like I said, it can be used a lot of ways in calculus, a lot of ways in differential equations, even some in linear algebra, things like that. Uh, but yeah, that's my related field. All right, so Chesney Culver here again, just to talk about my relative scientist. So the scientist I chose to talk about is Christian Huygens. He is a Dutch mathematician from the Netherlands, so his last name why it might look like Huygens or something like that, it is actually pronounced Huygens. So he was born and lived from 1629 to 1695. Like I said, he is from the Netherlands, so he's a Dutchman. He was a mathematician, philosopher, physicist, engineer, inventor. He did a lot of really cool things. Huygens studied law and mathematics originally. He was at the London University before continuing his education at Orange College in Breda, again in the Netherlands. Huygens is well known for a bunch of different things, a few of those things being he invented the first pendulum clock, which we'll kind of talk about here a little bit more in a second with relation to Hooke's law. Um, he is also credited with discovering Saturn's rings and its moon, the Titan. So, if you're familiar with a certain submarine here lately named the Titan, it was named after that moon that was discovered by Huygens. So, again, he is really famous for a lot of different things. Like I said, he was a mathematician. He helped pioneer the field of probability, which talks about how we can predict and certain outcomes based off of mathematics. So the probability of you striking it big at the casino, right? The probability of you winning the lottery, the probability of X, Y, and Z. Now, those are some basic examples, but just to give you an idea. Um, he is also credited with developing wave theory of light, and something that we've talked about in relation to Hooke's law is harmonic motion, simple harmonic motion, and the motions of waves, right? So anyway, those are a couple of different things that Huygens is credited for, what he's famous for. We have an image of him over here on the side from the European Space Society. So why is Christian Huygens important to our specific research in Hooke's law in general? So it's a little bit of a cool backstory in my opinion. There was actually an argument between Hooke and Huygens that debated who actually had the first idea of using a balance spring to maintain accurate time. So the way this is related to Hooke's law is Huygens is credited with this. He ended up winning that argument. He was given credit for this particular type of timekeeping. But what he basically did was create a real life example of Hooke's law, which was really cool. It was kind of the first tangible use of Hooke's law. And his idea was taking a balance spring and using it in a clock. Now, these springs are closely related to Hooke's law because of how they work. They use simple harmonic motion, which we've talked about before a little bit. That is kind of that wave motion. And these springs used Hooke's law, and we were able to calculate and kind of expect there are certain expectations of how their movements are going to happen, things like that. They were really resistant to really resistant to disturbances. Now, ultimately, Huygens was credited with the creation of these balance springs, these spiral balance springs, but it was, and which led to developments of better and more accurate timekeeping clocks and eventually the gravity independent clocks. But again, how it was related to Hooke's law is he kind of gave us the first tangible use of Hooke's law. He used the things that Hooke understood and Hooke learned and developed into that formula that we talked about, that F equals K or negative K times our deformation. And he applied that to real life and was able to use those things to give us a more accurate way of timekeeping. So Hooke is pretty much credited with the discovery of the law itself and the concepts behind it. And then Huygens is credited with the application of it, the application specifically in those springs used for those clocks. So that is my relative scientist related to Hooke's law, Christian Huygens. That's it, folks.
So I'm going to be reading the introduction. So the introduction of Hooke's law is a key principle in physics and engineering. It explains how materials respond to force. Robert Hooke introduced this law in 1660. It states that the force required to stretch or compress a spring is directly proportional to the distance it is stretched or compressed. And this concept is mathematically F equals kx. In the equation, F represents the applied force and K is the spring constant, which measures stiffness, and X is the amount the spring is extended or compressed. And the law applies not only to the springs, but also serves as a base for understanding elasticity, and various materials. So, for instance, bridges, buildings, vehicles, and even tissues like muscles and tendons follow Hooke's law when they are deformed. This principle helps scientists, architects, and engineers predict how materials relate to stress, which is for safety and effective for the design of it. So, Hooke law relates to areas such as physics, civil engineering, mechanical engineering, biomechanics, and material science. So, like rubber bands, as well as complex systems such as skyscrapers and airplanes. So that is the direction of Hooke's law. So I'm going to be showing the related fields of this stuff. So physics is Hooke's law and fundamental physics principles describing the relationship between force and spring extension. Engineering is one of the related fields. That's 2. 3 is materials science. That is the second one. And then we have biomechanics, civil engineering, mechanical engineering, and acoustics. Hopefully I'm saying that right. But that is all the related fields. In the introduction, I also talked about these fields as well. So that will be the related fields. So I'm going to be talking about one of the relevant scientists I chose. And it's Isaac Newton. So I'm going to talk a little bit about him. This is a picture of him right here. So Isaac Newton, he was born in 1642 and he passed away in 1727. He was an English physics, mathematic, and astronomer who made a significant contribution to science. He is the best known for creating the 3 laws of motion and the law of universal gravitation. So that's a really fun fact about him. These laws explain how forces act on objects and how planets move in space. And then he worked closely to Hooke's law because his laws of motion describe how forces such as those in stretched or compressed spring and create acceleration and balance. Although Robert Hooke first explained elasticity, Newton's principles provided scientists with the basics to understand the motion of force fully. So he was similar to Hooke, but he is Isaac Newton, so he does have similar stuff when it comes to physics. So that's about Isaac Newton.
Hi, my name is Luzman. I will be giving my introduction about Hooke's law. This is all physics. In physics, this is a law that states that force needed to extend a spring or compress a spring by someone's distance is proportional to that distance. And on Hooke's word has the extension, so the force. This law studies vibration, behaviors of materials under stress, and also studies elastic and non-elastic materials. And some elastic materials can be extended or compressed and then recoil or return to their original states. Non-elastic materials, according to this law, can change or break when force is applied. Force can be something like stretching, bending, and twisting, or squeezing. And related fields with this law is related to mechanical or digital clocks. This law gave the principle to use balance wheel that is used in clocks. The structural in mechanical engineering is also one of the fields that help to understand behaviors of vibration and how beams and suspensions systems works. This law is also crucial to design springs, building bridges and structures that can support stress. In acoustic and seismology, this is the study of vibration, understanding of musical instruments, and how sounds propagation works. Also, excuse me. Also, in the molecular level, thanks to the understanding the elasticity, help to characterize and classify the skins, and also to design and make prosthetics limbs that are capable to withstand stress, and many other equipments that are used in the medical field that have some certain elastic characteristics or elastic elements in it. And this law helped to create or understand detecting electrical design the springs, and how the electrical currents works. And relevant science, I'm gonna be talking about the scientist Robert Hooke, that he formulated the elasticity law, known as Hooke's law. He was born on July 18th in 1635 in Isle of Wight in England. He died in March 3rd of 1703 in London. Hooke was a scientist. He also was a physicist and a polymath. He formulated the elasticity law that I mentioned before, the Hooke's law, in 1960. His education, he attended London Westminster School and Oxford University. He worked with the chemist Robert Boyle to help him to build air pump that Boyle used for his experiments on gas law. He gave a huge contribution in microbiology and studies of cells. He wrote a book called Micrography, where he detailed what he called tiny box-like structures that we know today as cells. For his understanding of elasticity led him invent the balance springs used in portable watches. Hooke also suggested the inverse square law for gravitational forces, orbitational motion, that later Newton proved and formalized. He also was known as an architect, and one of his contribution in this field was the redesigning and the building of the Great Fire in London in 1966 that is still up to date. That's all for now. Thank you.
Hi, my name is Zakia Duncan, and I'm going to give you some basic facts and information, some related fields, and relevant scientists to Hooke's Law. So, some basic facts and information. Hooke's Law was named after Robert Hooke, an English scientist who discovered the principle in 1660. Hooke's Law describes the relationship between the force and the stretch of an elastic object. Basic definition: an elastic limit is the max amount that can be stretched. Beyond that point, the force and the stretch are no longer proportional. Now, for some related fields, biochemistry uses Hooke's Law quite a bit. Biochemistry is the study of the chemical processes and the substances that occurs in living organisms. The DNA strands and proteins and cell membranes behave like tiny little springs. And when the forces stretch or twist or compress the biomolecules, like DNA replication or protein folding, they can deform and return back to their original shape. Scientists use Hooke's law to model the elastic behavior, which allows them to calculate and understand how molecules maintain and shape their stability. Now, for relative scientists, we're going to go over Robert Boyle. Robert Boyle, the father of modern chemistry, had Hooke as an assistant, helping with the design of the air pump, and leading to Boyle's law. The collaboration trained Hooke in experimental and mechanical design, and which led to Hooke's law. Boyle's influence and mentorship had helped shape the foundation to Hooke's own discoveries.